So now we're going to do a 3D angle problem. So 3D angle problem. And the goal here is for us to find theta x, theta y, and theta z, which are the direction angles for each one of these forces. Let's take a look at F4 first. So we know the magnitude of F4 is 4 kilonewtons. So the first thing we have to do is just first thing what do you do on a 3D problem? What do? Take a look at the axes. Here's the x-axis, here's the y-axis, the horizontal plane, and here's z. As we go along in statics, so far we're looking at two 3D problems, and both of them have the axis set up the same way. But that's not the case in all the statics. We're going to see different axes, so we always have to make sure we know where the axes are. So look at F4. Can you picture that in 3D? Can you see that? Where does F4 lie? Where does F4 lie? Can you see that F4 has no component in the x? Can you see that the F4 force lies in the YZ plane? And it has a negative value in the y, and it has a positive value in the z. Can you see that? So F4 lies along on the YZ plane. So if we wanted to find out what, let's look at the one that's given. What is theta z? That 30 degrees there. Is that theta x, theta y, or theta z? It's theta z. And the reason why is it's the angle that's between the force in question and the positive z-axis. So what does that mean about theta y? Well, we just said that it lies on the YZ plane, so shouldn't theta y be this angle right here? It's the angle between the force in question and the positive y-axis. So what is that? This right here is a 90 degree plus 30, it's 120. So it's 120 degrees. How about theta x? If F4 lies on the YZ plane, what is its angle to the x-axis? So let's take out this guy again. Here's the x-axis, the y-axis, here's the z. The force is here. If the force lies on this plane, isn't it perpendicular to the x-axis? It's perpendicular to the x-axis because anything that lies on this YZ plane is perpendicular to the x-axis. So it gives you 90 degrees. So let's set up our components. F4 is equal to 4. Put kilonewtons out here. The cosine of 30 degrees I plus the cosine of 120 J plus the cosine of 90K. And what does that come out to be? 4 times cosine 30. I always get, is it 0.5 or 866? 0.5. So it is, oh, I just put it in the wrong order, didn't I? This is supposed to be theta x. This is theta y, and this is theta z. Did you catch that mistake there? So what is the cosine of 90? 0. Does that make sense? Yeah. Because that force F4 has no component in the x-axis. So it's 0 y. And then cosine of 120 is a negative 0.5. And remember, we have to carry it out to 4 decimal places because that's the rule for unit vectors. Plus 0.8660 K kilonewtons. And it turns out to be negative 2.0, of course, J, plus 4 times 0.8 is 3.5 kilonewtons. How did we represent this? We represented it in vector form. What's the other way? Represented magnitude and direction angle. So let's write that. Magnitude for kilonewtons, magnitude and unit vector. So the unit vector, let's say E4 is equal to negative 0.5000j plus 0.8660k. Magnitude and unit vector, and then magnitude and direction angle. Direction angles, we already know. This is 90. Theta y is 120. And theta z is 30. And how do we do our checks? Our checks are, I've been doing it in red, so I'll do it in red. Negative 2 squared plus 3.5 squared under the radical equals 4. Okay, that's our magnitude check. 0.5 squared plus 0.866 squared. Doesn't need to be under the radical, because under the radical 1, under the radical is 1. We checked our unit vector, and then we can also do this cosine squared theta x plus cosine squared theta y plus cosine squared theta z equals 1, and it checks. And what's the last check? So these two are both unit vector checks. What's the last check? We want to do a visual, positive and negative visual check. So let's see. We've got a negative value in the y. Take a look at a picture. Yes, it should be negative. We've got a positive value for the z. Yes, and we got a 0 for the x. So this is okay. So 1, 2, 3 steps. That's all I want to see it in. 1, 2, 3 steps. Okay? And then make sure you do your magnitude check, your unit vector check, and your visual check. Okay. I'm going to erase this, and we're going to do a different problem. Sorry, a different force. Let's see. Let's do F2. F2 is given as 6 kilonewtons. Again, it's a 3D angle problem. We're trying to find out what theta x is, what theta y is, and theta z is. So what angle did they give us? They give us 40. So take a look at that in 3D space. It's the angle between the force in question and the positive x-axis, so that must be theta x. Can you tell that F2 lies on the xz plane? The xz plane? It lies on the xz plane. So that means this angle right here, from the force to the z, would be 50 degrees. Be careful, because I know you know that a right angle is 90 degrees, but a lot of times we're kind of prone to think about 100, and a lot of times students say, oh, 40 from 160, this is 60 degrees. Remember to just keep checking yourself and make sure that you're subtracting things from 90 and not 100. And then if it lies on the xz plane, then it's perpendicular to the y. So this is 90 degrees. Okay, F2 equals 6 cosine 40 times I plus cosine 90 j plus cosine 50k kilonewtons. Looking at this, we're getting all acute angles. Notice these are all, well, I guess this is not, but this one and this one, they're both acute angles. What's that telling us? It's telling us that we're going to have positive values, because our force is acute angle to the axes. So let's see, cosine 40, let's see which one this is, F2. You probably got the values right. Okay, F2. Oh, hang on. Okay, what's cosine of 40? I'm going to have to do it. 0.7660I plus, this we know is 0, J, plus 50. 50 cosine 0.6428 K kilonewtons, and F2 turns out to be 4.6I plus 3.9 K kilonewtons. This is represented in vector form. We do our check, 4.6 squared plus 3.9 squared under the radical should equal 6, and it does. Then we can do the magnitude of 6 kilonewtons, and the unit vector of 2 is 0.7660I plus 0.6428 K. So that's the magnitude and unit vector. And we could do a check by saying 0.766 squared plus 0.6428 squared is equal to 1, and it does. And then the angles, the magnitude and the direction angles, which we already have. F2 is equal to 6 kilonewtons, and here are the unit vectors, and we could check those too. We could say the cosine squared of 40 plus the cosine squared of 90 plus the cosine squared of 50 is equal to 1, and it does. And the last check, positive, negative visual check. We got a 0 for the y, we got a positive for the x, and a positive for the z, and it does check. Okay. Okay. So I'm going through step by step a lot of problems on making sure that you're comfortable finding components. And I know you did it, in physics already and probably in math as well. But I really want you to be efficient, because this is not the main part of the statics. The main part of statics is making sure things that don't collapse, things that stand still and they can support their loads. We're preventing failure in engineering. But in order to do that, we need to find components, so I wanted to do it in a quick way so that we could get through that part of the problem and move on to the statics part. Let me see what other things I want to talk about before we end all of this. Yep, the rest we'll do in static. So let me just pull, I'm going to open up, let me pull down the I'm going to show you where everything is on the web. Okay, so what I did is I went to my website, which is cabrillo.edu. /Tilda J. Panzardi, and I clicked on Engineering 35, and in 35 I still haven't updated the syllabus yet, so you're going to have to wait until I get back from Guatemala. You know that we're taking the Engineering Abroad program leaves tomorrow, so I'll have the syllabus up then. But in the meantime, what you want to see is the packet. The packet gives you different units we deal with in statics, and we'll look at that on the first day of class, and different math that is important, geometry and trig. Trig is so critical in statics, so if you're a little rusty on trig, definitely practice. And then it moves into information about what the dot product is, which we talked about already. And then it goes into these 4 problems that we worked through already. Actually, you know what? We still need to do one more problem. We need to do some of the F1, so let's do that too. And then the homework, I'll let you know which problems you need to do. Okay, so we have to come back to this problem. So we're going to zoom in. And I'm going to pull this back up. Let me erase this, because we didn't do that last time. Okay, here we are. Okay, so we did F2 already, and we did F3. F4 and F3 I don't think we need to do, it's only going in the Z direction. But this one's a key one. So as it was, let's take a look at these two. So let's look at F4. So here's our x-axis, our y-axis, and Z. And F4 was pointed in the negative y direction and the positive z, and it was in the yz plane. This force, F2, was in the xz plane. It was lying in the xz plane and therefore 90 degrees from the y-axis. Let's take a look at what's going on here for F1. X-axis, y-axis, z-axis, and this, F1, is going into that first octant. And the angle that they're giving us is 40 degrees. It's giving us a 40-degree angle that's projected down onto the xy plane. Are they giving us theta x? No. Are they giving us theta y? No. Are they giving us theta z? Well, if we know it's 40 degrees to go down to the plane, then this right here must be 50 degrees. Right? So they are giving us theta z, but they're not giving us theta x, and they're not giving us theta y. So we have to figure out a way of finding out what the x component is and the y component is of F1, because they don't give us what theta x and theta y are. They give us the 40 degrees down to the xy plane, and then they give us 50 degrees to get to the x-axis. So now, what we have to think about is the dot product. We know now that no matter where our force is, if we know the angle to an axis, we can find the component of that force. So if I take the magnitude of this force and multiply it by the cosine of that angle, I could find that component. If I take the magnitude of the force and multiply it by the cosine of the angle here, which happens to be 40 degrees, I'm finding the component of this force in this direction. Let me say that again. If we take the magnitude of this force and we multiply it by the cosine of 40 degrees, I find the component of this force in this direction. If I have a force over here and I know what the theta z is, I multiply this force times cosine of theta z to find the component of the force along the z-axis. So the angles, using the angles with the cosine, is basically our dot product. So let's look back here. We're looking at F1, which is 5 kilonewtons, theta x, theta y, and theta z. So where is theta x? This is the force. Theta x would be this angle right here. It would be this. And they don't give it to us. We don't know. Theta y. Theta y would be this angle right here. This is y. this would be my theta y. Theta y, theta x. They don't give it to us. But they do give us a theta angle of 40 degrees going down to the xy plane. So therefore, this angle right here is my theta z, and that's the only one that's given. And let's say it's 90 minus 40. It's equal to 50 degrees. So, can you figure out how we can find the x component of this force? Only knowing this angle and knowing this angle. Think about dot product. If I take 5 and I multiply it by the cosine of 40, I find the projection, the component of this force along this direction. If I then take that value and multiply it by the cosine of 50, aren't I flipping it over here? So I could find the component of F1 in the direction of x by saying 5 times the cosine of 40 times the cosine of 50. So let's do it with the PVC pipe. I take this force, the value of it, the magnitude of it is 5. Multiply 5 times the cosine of 40. I now brought the force here. Then I take that value and multiply it by the cosine of 50, and now I found the x component. How about the y?